either in the question or in the answer. So if you want to grab, I don't think you need a calculator today really, but if you just want to grab the pencil, go ahead and put your computers up, pretty please. Aditya, that's you too. Thank you, sir. All right, on our first set here, our first instruction just says an infinite limit is a limit in which f of x increases or decreases without bound as x approaches c. And then before we even get to like official problems, there's just one here I want us to kind of feel out. This is a graph that I know might be difficult, but we would expect you to know how to do that without a calculator. It stems from the parent graph of 1 over x, which is quadrants 1 and 3. But it's been shifted to the right 2, and it's 3 times taller. So what that means is if I was to sketch a graph of this, there would be an asymptote at 2. And then 3 times taller is kind of hard to draw, but your graph would look like that. And that's something we kind of covered that first review week, is you have to know those like 12 or 15 basic functions and how to adjust them to get the graph that we're using for the equation. Then we're asked about the limit as x goes to 2 from the right. So that means from the right of 2, which is here, I'm looking to see what's happening at the y value there. And the y value there is going to be positive infinity. Then I'm also going to look to the left of 2. So I'll look at 2, I'll look for values smaller than 2, which is here. And that arrow is going down towards negative infinity. And on one-sided limits, it's okay to leave your answer like that. But then when you have an overall limit, your technical answer does not exist because the limit is infinite. So in this case, it's going to both positive and negative infinity. So you technically could put 2 because statements there, one of which is that it's going to infinity, and the second would be that the left limit and the right limit don't equal each other. Like it's extra does not exist because of 2 reasons. So right now we're saying like, okay, if we had a graph, we could tell when an answer was infinity because we'd be able to look at the asymptote, the vertical asymptote. But then I'm going to challenge you to say, well, how would we know that if we didn't have the graph? How would we figure that out if we didn't know what that graph looks like? Because you might be in a situation where you don't remember the graph. Do you guys have answers to that thought or question?
I was gonna say, like, if it's 2 from the right, you can plug in like 2.1.
Yeah, that's exactly what we're going to do. Okay, good. That's perfect segue. Did you have a question? No, or just the same kind of thought? Okay, so I want you to recognize, like, when you go to plug 2 into the denominator, you get 0. So anytime that you have a number divided by 0, that is not a work harder situation. Like, work harder is when you get 0 over 0. But if you get a number divided by 0, your answer is either going to be infinity or negative infinity. It's one of those 2. And the way you check is you do what's called a sign test. And I'm going to show you what that looks like. So today we're focusing on what if we get a number divided by infinity, how do we handle that? So number over infinity. So if I do 2 from the right, if I directly substitute 2 into my equation, I end up with 3 over 0. Okay, so I know my answer is going to be infinity or negative infinity. We already know it's going to be positive. But how would I know that it was positive without having looked at the graph? And that is by picking a value slightly bigger than 2. So I would suggest 2.1. And I plug 2.1 into my expression and just look at this sign. I don't need to know the decimal. I just need to know the sign of what you get when you plug in 2.1. So if I plug in 2.1, I get positive on top. And if I plug in 2.1, I get positive on the bottom. And that sign test then tells me positive divided by positive is still positive. So that's why I had positive infinity as my answer. Okay, second one, 2 from the left. So I'm thinking of something a little bit smaller than 2, so like 1.9. So now what I'm doing, I mean, I know this went to 3 over 0, right? We already kind of established that plugging in 2 gives a 3 over 0. But now I have a left-hand limit, and a left-hand limit is something smaller than 2. So if I plug in 1.9, and again, I don't need to know the decimal. I just need to know, will it be positive or negative when I plug in 1.9? So if I plug it up here, so I get positive 3. If I plug in 1.9 down here and subtract 2, that will be a negative value. And a positive divided by negative is negative. So again, if you have the picture, you're just looking at the picture. But if you don't have the picture, now you have this skill of figuring out positive or negative infinity by checking just by plugging to the left or the right. Now your overall limit, so like for this question, you have to check both, left and right. And you get both, positive and negative. So that's why we have, because it goes to positive and negative infinity. Okay, so let's try some more of this. So on all the rest of these graphs for this section, equation, all the rest of these equations, we're not going to know what the graph looks like. So we're going to practice doing this strategy without having the graph to refer to. So start out, plug in the number, direct substitution. Oh, I get 3 over 0 again. In this case, 3 over 0. So that tells me my answer will be either positive infinity or negative infinity. But I'm going to plug in to test, sign test, which one it is. So to the right of 1, I'm going to plug in 1.1 and check my signs. I plug in 1.1 to the numerator, I get something positive. If I plug in 1.1 to the denominator, I get something negative. And therefore, my sign test tells me that my result will be negative. And overall, I'm going to get negative infinity. This is the part that tells me it's infinite. This is the part that tells me if it's positive or negative. Okay, second example. Okay, so this one has 2 different pieces. I'm going to plug into both. So if I plug in 0, I get 0 minus 1 over 0. I don't have to plug in here because I already know that's 0. I have to plug in here to sign test that spot. Like, I'm just going to look at this and sign test that spot. So to the left of 0 would be like negative 0.1. So I'm going to plug in negative 0.1. The top still gives me a positive 1. The bottom gives me a negative 0.1, so negative. It gets a little weird. So the negatives are a little tricky here. So just be careful. You have the negative where you subtract, and the negative on the bottom, so like minus a negative will overall end up being positive. It's like having 0 minus negative infinity is 0 plus infinity. So this one is positive infinity. Just because there's like 2 negatives. There's the negative from the fraction part and the subtraction up front. Question. Oh, good question. So the question is, do you have to do a decimal like that, or could you just plug in like something you know is to the left? I would encourage you to plug something that's close, within like 0.5, because sometimes you'll have a graph with like an asymptote here and an asymptote here, or a hole here, or like something happening somewhere else in the graph that will impact what you get. So you want to be close. You don't have to be at 0.1, but be pretty close. And honestly, in all these, really, when you're plugging in, if you don't need to get the exact decimal, you're just checking to see if it's positive or negative. Ellie, question? No, we only have to sign. So the only place you have to sign test is where you get a number divided by 0. So this didn't have that. That part worked for direct substitution, and I'm just handling differently the fraction. The question was like, why didn't we sign test on that first part? And we didn't have to, just where you have the fraction. Okay, third example has trigonometry in it. So we got to figure out how we're going to handle that. So this is the same thing as the graph of -2 cosecant or -2 secant, excuse me. So if you like wanted to graph in your head -2 secant, you could figure that out, or just let's try our strategy. So plug in the pi over 2. Pi over 2 is here. That order pair is 0, 1, and it goes cosine sine. So the cosine value of pi over 2 is 0. That means I'm getting -2 over 0, which means I need to do my strategy. So my answer will be either positive or negative infinity. I've just got to figure out which. So when I go to plug in to the right of pi over 2, there's 2 ways you can consider this. I'll show you both. But to the right of pi over 2 means an angle bigger than pi over 2. Now you could say 3 pi over 4, but like I'm not even going to get that complex. Just something bigger than pi over 2. So when I look at my unit circle, pi over 2 is here. Something bigger than that would be over here. I know that looks like it's left, and we're doing a right-sided limit, but that's because we're looking for something bigger than pi over two. And then if I go A, S, T, C, cosine in that particular location is negative. So when I'm sign testing, I get negative for the bottom part. If I plug in something bigger than pi over two in that location, cosine is negative. And then on the top, it's -2, so it's just always negative. Questions?
Does it have to be cosine? Because it doesn't work with like 5 pi over 3 or something.
Yeah, no, if you had been given an angle that was down here in the fourth quadrant and you were going to the right or left of that, cosine would just be positive there instead of negative. So like, we're just using that graph to sign test is all. Question.
So we don't actually have to find like any number to find out the
Right.
other variables.
You're not finding the value, you're just checking the sign. Yep. If that didn't make sense to you, another way you could look at this is like, that's your cosine graph, high, middle, low, middle, high. Pi over two is here. If I go to the right of pi over two, so like just a little bit bigger than pi over two, my result is negative. So you can either look at the graph of cosine at bigger than pi over two, or your unit circle where cosine is bigger than pi over two. And in both cases, you should see that cosine is negative, and then a negative divided by negative overall is positive. It's a hard one. Okay, letter D is we're start out direct substitution. I get 16 over 16 plus 16. That gives me 16 over 32, which means I'm not sign testing in this case at all. You only do the sign test if you get a number divided by 0. Okay, and then kind of like in summary, everything we just looked at is when you have your number divided by 0, in most cases, you're looking at a vertical asymptote. And so you're just determining like, is the asymptote going up? You know, like is the graph approaching the asymptote positive infinity or negative infinity? And so if your function is going to either positive or negative infinity from the right or left, that is a vertical asymptote. And you guys did a lot of like end behavior in your previous math classes. So these are all places where you would have, you know, an infinity or negative infinity on your graph. Okay, second thing we're gonna do here is practice with the vertical asymptotes. This should be hopefully a review. And so as a reminder with vertical asymptotes, you're gonna factor first. And then you're gonna check and see if the denominator cancels. So does the denominator cancel or not? And whatever's left, take the denominator equal to 0. Okay, so example 2A, find the vertical asymptotes. This does not factor, so I don't have to do that first step. Take the denominator equal to 0, and that tells me the vertical asymptotes at 2. On letter B, the denominator does factor, but the numerator does not. Question. Yep. And so I put each of those factors equal to 0. And then letter C, in this case, both the numerator and the denominator factor. So I can do a greatest common factor on the top. And then just difference of squares on the bottom. Okay, then this cancels. Okay, remind me what that is again. A hole in the graph. Very good. That is a removable discontinuity. Hole in the graph is a removable discontinuity. I'm left with 3 over x plus 5. Now I take my denominator equal to 0. Oops. And your answer is -5. Okay, so hopefully, like I said, hopefully that's review. Those first 3 should be like, ooh, okay, know how to do that. Then letter D is trig, so we have to look at that probably a little more closely. If you look at this as the fraction cosine over sine, so like use your cotangent identity. And then nothing cancels there, so I take the denominator equal to 0. And then that's asking me, where does sine equal 0? At what angle does sine equal 0? Yes. Or question? 0. Okay, 0 is correct. Yep. Anyone have another one? Pi. Very good. Anyone have another one? 2 pi. Good. Question?
Don't you default principles or whatever?
Yep. Okay. Awesome. So excellent. Okay. So the question was, don't you have to follow principal values? And yes, if there's not a domain given in the directions, the only answer we're going to put here is 0. Now, last year, your answer would have looked like this, because principal values wasn't used as much, right? But like this year, we're going to say, like, we're not doing infinite answers. We're just going to stick with principal values. And principal values is only give the answer from negative pi over 2 to pi over 2 for sine. And so that's the only answer we have to give. Principal value is really supposed to make it simpler. You just have to remember it, but. Okay, so vertical asymptotes, you got a couple of questions like that on your classwork today, so that part of it should be easy. Okay, before you flip over, this bottom table is pretty important, so I want to chat about that. It looks a little hard to understand. Okay, this table is kind of going through the properties of what you can do with infinity. So infinity doesn't count as a real number. It's like a concept, right? Like it's not an actual number that you can work with as a regular number. So this says, so like, let's assume f of x is infinity and g of x has a limit of like a regular number. Well, if you add or subtract infinity plus a number, you're still going to get infinity. And you might argue, well, like, oh, well, that's a bigger infinity. But infinity is just a description of an infinite number of values. Okay, so it's not that it's a bigger or smaller infinity, it's just still uncountable. Okay, an uncountable set. And then if you multiply infinity times a number, you're still going to get an infinity. And if you multiply infinity times a negative number, you just get negative infinity. And then here, if you take a number divided by infinity, that is going to go to 0. That's what this one is saying. We talked about that yesterday in class. It was like, oh, hey, I have $1. And I split it up among everyone in the earth. And we did not get very much money from that. We all got 0, right? So like any number divided by a very large number is going to go to 0. And then the opposite of that is any number divided by 0 goes to positive or negative infinity. We have to sign test to check. So this is like, as we're doing limits, we use these properties. I really should have like an arrow in here instead of equals, but arrow. What was that number divided by 0? Okay, questions on that side? All right, let's flip over to the other side. And the top 2 questions on there use the 2 properties we just talked about. So let's kind of go through what that looks like in a limit scenario. It's just kind of the same thing we've been doing, but now we have like concrete rules to say it. So start out first here, I do direct substitution. I get 1 over 0 squared, which is just 1 over 0. And then this is where I'm like, okay, my answer is going to be either infinity or negative infinity. I have to test to see which, but this is both sides. So I got to check both. So to the left of 0, I'm going to plug in like negative 0.1. And to the right of 0, I'm going to plug in positive 0.1. The good news is that those both are then just squared. So they both turn to positive. So I'm going to kind of do these both at once. Either one of those, if I plug in, is going to give me a positive on the bottom. And of course, the top is still positive. So then my test tells me I get positive infinity minus 5. And my properties I just learned about on the other side says if you have infinity minus 5, it still counts as infinity. Because this is an overall limit though, and it's not one-sided, my technical answer is going to be does not exist. because we approach positive infinity. On a one-sided limit, you wouldn't have to put, that does not exist, but overall limits you do. Yes, question.
So in our answer, let's put infinity or infinity minus 5.
Infinity, good question. Yep, so this is what that property on the other side is saying, like, if you add a constant to infinity, you still get infinity. Okay, and then letter B here, I know you probably could do this a simpler way than what we're about to talk about right now. But we're gonna roll with it so we can talk about the properties. So this is our big division bar right here. So could we do a keep change flip? Yes, we could. And we'll get the same answer, but we're gonna go through it just so we can talk about the properties a little more. But I'm gonna direct substitute first and plug in 1. Gives me 2 over 1 over 0. And then this part, I have to sign test so I can tell if I get positive or negative infinity. So I'm going to plug in to the left of 1, which would be like plugging in 0.9. 0.9 on the denominator there, minus 1. That'll give me a negative on bottom. And then, of course, 1 on top is still positive. So my overall result here is negative infinity. And we kind of talked about that property on the other side. Any number divided by infinity goes to 0. So this result is 0. You could get that same thing by doing a keep change flip and plugging in. But I just wanted to show you an example where you had like a fraction within there. And then you had to look at that fraction rule. Okay, questions so far? It's kind of a weird day. Like, I don't mean outside, but I mean like a weird day of notes where we're just like plugging in numbers and approximating it in our head instead of doing like the actual calculation. Okay, we are going to, I was in my last class, we took a little break here so we could like wake up. But then in my last class, we didn't have enough time to finish stuff. So we're going to power through the rest of this page. So I need you to like bear with me. I saw disappointment in your faces. It'll be all right. We're almost done. Okay, so kind of like switching gears for a second. Everything we did so far was like limit as x goes to a number, and our result was either positive or negative infinity. And now we're going to reverse that. We're going to say, what if the limit goes to positive or negative infinity? So we're just like going to consider what if infinity is in a different spot. Okay, so first of all, I want to review with you really quick. Math 3, horizontal asymptote rules. What we did with those is we would look to see if something's top heavy, bottom heavy, or the same. So I want to review that real quick. If you have something top heavy, there is no asymptote there. Or maybe you just put none. I don't know. No horizontal asymptote. If you have a bottom heavy expression, your asymptote was y equals 0. And if you had an expression where the exponents are the same, you did the lead coefficients, a over b. Okay, does this sound familiar to you? Yes, okay, good. Okay. So when a question asks you, what is the limit as x goes to infinity? That is the same thing as saying to you, what is the horizontal asymptote? And that's why you spend all this time doing end behavior in your previous classes, just so that you can understand what this is asking you. So this is saying, what is the horizontal asymptote at positive infinity? And you do not have to do any different calculus work. You're literally just going to follow the same rules you learned in your other classes to get your answers. Now, there is a way you can do it with calculus, and I'll show you that. But these shortcuts give you the exact same answer. So we're just going to follow what you already know how to do to make it easy. Okay, so first example is asking for horizontal asymptote of this. Now, 5 is not a fraction. So I'm just going to leave that. It's like 5 minus. And then I have a bottom heavy fraction. And a bottom heavy goes to 0. So this works out to be 5 minus 0. Overall, my limit is 5. My second fraction, I look to see if it's top heavy, bottom heavy are the same. These are the same power. So I use this rule. I do my lead coefficients, a over b. And so it's like a 2 over 1 overall. That is just 2. Question? Okay. Okay, third example is bottom heavy, because x and x squared. So x squared is bigger, bottom heavy gives me 0. So this would just be 0. These are the same. If your exponents are the same, you do the lead coefficients. So this is going to be 4/3. Okay, and then letter E, when I get to that one's top heavy. For something top heavy, it's going to be it does not exist because there isn't an asymptote. Okay. And then I don't know if this will go to positive infinity or negative infinity, but I can tell by sign testing by plugging in just a big number. And again, I don't need to know exact values. I just need to know the signs. So if I plug infinity in up here, I'm thinking like 4 times a really big number minus 1 would be positive. And then 3 times a really big number plus 5 would be positive. So my result is positive infinity. And you only have to verify that when you've got something that's top heavy. Because all the rest of them are either just 0 or the number. Okay, and then letter F, that is not a polynomial, so it doesn't really count when you're looking at top heavy, bottom heavy are the same. But I can just do a direct substitution of my infinity. And e to the infinity is still infinity or infinite value. And then that's one of my rules. If I have a number divided by infinity, this goes to 0. I know it does kind of look like it's bottom heavy, which you can think of it that way. You're putting a really large number in the denominator. $3 divided by everyone in the world goes to 0. And then kind of our summary here is that if you have a limit going to infinity or negative infinity, then that's your horizontal asymptote. We still have to talk about the negative infinity, which we'll do that next. But something you don't have to write down, but I want you to listen to, is the way these shortcut rules were like explained to you is just like, oh, just learn these, right? Like just learn these. They came from calculus, like from doing limits. So you were kind of learning like steps in calculus without knowing what it is you were doing. And these all work because the process, the calculus process we would do to solve these is you divide everything by the biggest power of x in the denominator. So I'm just going to show you one quick example. Like the biggest power of x in the denominator, if I divide everything by x squared here, I get 4 minus 1 over x squared. 4 minus 1 over x squared, and then 3 plus 5 over x squared. And if I direct substitute the infinity in, both of those fractions go to 0. This goes to 0, that goes to 0. So I just get left the lead coefficients. And so the rule you learned about lead coefficients comes from that if I divide by the biggest power of x, the only thing that won't have a denominator is the lead coefficients. And so you kind of learned that rule as like a shortcut, and we're still even going to use it now as a shortcut, but it comes from the calculus of doing that limit. Okay, I know I'm talking for a long time. Y'all are looking tired, but we're almost done. It's Friday. Yay, yeah. I like it. Okay. All right. So on the last of these examples, this one and this one are the same problem. The same problem, but one's positive infinity and one's negative infinity. So we're going to do it once like normal. And then we're going to talk about what do we do if we have a negative infinity. Okay, so do this one like normal. We just talked about top heavy, bottom heavy are the same. This right here in front means check horizontal asymptotes. And it's kind of hard to tell the horizontal asymptote because you've got this radical on the bottom. So if I just look at just the x's, you really have to think of this as square root x squared on the bottom. Now I know there's a 2 and I know there's a 1 there, but like a square root has to do with your exponent. And when I'm looking top heavy, bottom heavy, I'm looking to see what exponent is bigger, and square root x squared is still just x. So these are the same. This is like having x over x. And when you have the same, you do the lead coefficient. So my lead coefficients here would be 3 over radical 2. And you do not have to rationalize. So lead coefficient there is 3, lead coefficient there is radical 2. So it's kind of a weird one, but so that's one horizontal asymptote, no problem. But if they give you this is asking for the horizontal asymptote on the left. This is like left-hand behavior. And if you have a left-hand behavior, you're going to do your horizontal asymptote rule just like normal, but then you're going to sign test. Okay, so left hand and behavior requires a sign test. Just one extra step. So I do my limit like normal. We said these are the same exponents. So lead coefficients. So I know my answer is going to be 3 over radical 2, but then I have to sign test because it's left hand and behavior. And sometimes your functions point arrows in opposite directions, right? Like sometimes they're the same, sometimes they're opposites. So on the left, to sign test, I'm plugging in just a big negative number. And you don't have to get the exact numeric value. It's like, okay, so I'm plugging in negative 5,000 or whatever. So plug in a negative number on top, minus 2 is going to be negative. On the bottom, if I plug in a big negative number, but then square it, be positive, times 2 plus 1, still positive. The square root doesn't change the sign. And by sign testing, I can tell that I'm going to get a negative. So left hand and behavior, you do the same way. You just also do a sign test at the end. I mean, it wouldn't hurt to do a sign test on every single problem if you wanted to, but you don't need to unless it's left hand and behavior. Allie, question? It made it negative instead of positive. So like when we did this problem originally without negative infinity, when it's positive infinity, we got positive 3 over radical 2. And when it was negative infinity, we get 3 over radical 2, but then we sign test to get the sign of that.
Why can't you just like solve it for x goes to infinity and then take the opposite sign?
Because it does always work out to be the opposite. Okay, good question. So the question was like, why couldn't we just solve that and then just switch the signs because of that, right? What if you had 3x squared over square root 5x to the 4th? When you plug into that, you still get a positive, like positive or positive. In this case, we got a negative or positive. So it's not that it's always the opposite. It really just depends on if your function, I don't want to say symmetry because it's not necessarily symmetric, but it depends on if the behavior on the right is identical to the behavior on the left or it's opposite directions. Opposite number.
You can see that like based on like what power it is to, right? Like if it's even or odd.
Yes, yeah, you could do even and odd. Yes, okay, so that, like, could you relate this to like even and odd testing to then figure out if the signs are opposite? Absolutely. I've seen that takes longer, but yes, you could. And like, we don't want to do even and odd testing on that. Like, but we could, yes. Yes, you're correct. Kevin, do you have a question? See, you know. What if there's a decimal? Oh, then you would just write it as square root of whatever the decimal is. Well, your son's looking at the sign, even if it's a decimal.
I mean, like the brown, like, for example, it's like 40.
Oh, you're saying like,
Oh, yeah.
this is 1.46?
No, the x on square. So you can square like a like 0.5 like x to the 1/2. I mean like it's like using it.
Oh, you're saying if the power is a fraction. Oh, even, well, you can't take even powers of negative numbers, so that wouldn't be a situation that would happen anyway. But if it was a third in there, odd roots keep the same sign. So if you plug in a negative, you get a negative out. Okay, any other questions? All right, our last two, are real, they're not gonna follow horizontal asymptote rules. This is kind of going back to what we did a day or two ago to just help us remember. Okay, so last two. I look at the limit as x goes to infinity. In my mind, I want to do a horizontal asymptote. When you see that, I want you to think horizontal asymptote. But this is not going to have a horizontal asymptote. Sine is your middle, high, middle, low, middle, and like repeats, right? So your sine graph does not have a horizontal asymptote. But if I think about what's happening to the y value as I go to infinity, it also doesn't go up infinitely or down infinitely. It bounces back and forth from 1 to -1, 1 to -1, 1 to -1. And it's been a while since we talked about this, but that's called oscillation. Not equals. Okay, it does not exist because the graph oscillates. I'm going to put oscillation. So if you have something that doesn't have a horizontal asymptote and also doesn't have an end behavior like a trig function, you just have to think about what's happening. So there's no like formula here. It's just realizing sine or cosine bounces back and forth between numbers. Question.
Can you abbreviate your oscillation?
I would not. I would not. Okay, the question was, can you abbreviate oscillation? So if you abbreviate really anything, then it's up to the reader to decide what they think you're abbreviating, because there's a lot of math words out there that we don't know yet. And people put all sorts of stuff on AP exams and tests and stuff. I would not abbreviate. It only takes a second longer to write it. Write it out. Even if you spell it wrong, that's better than abbreviating. Because I'm not a good speller either. Yes, question.
So, trying to find horizontal.
Right.
So it doesn't like sine in like a deep and it comes like just consistent. Doesn't cause.
No, that's not a horizontal asymptote because asymptotic behaviors, it gets closer and closer and closer to that number, right? But it is bounded by 1 and -1. So it does have like a maximum and minimum value that it stays in between, but it's still not asymptote because it would have to like approach that number instead of then going down and back up again. All right, our last one is, do you remember that day that we did the squeeze theorem in class and we went from like easy ones in class, so then there was a really hard one on that worksheet? Do you remember that day? Okay, we're gonna practice another one of the hard ones. Okay, did you have a question before we go on? Yeah. Okay, so this problem is not our identity. The identity of 1, like sine x over x going to 1, that works if this is a 0. So it's not that. So it'd be nice to be like, oh, it's 1, done. I already memorized that, good. But it's not that. So what this is asking for is a horizontal asymptote, but you have no idea what that graph looks like. So I don't know what the graph looks like. Then I've got to try my rules, like top heavy, bottom heavy are the same. But when you do top heavy, bottom heavy are the same, I don't have polynomials, so I can't really look at the exponents. I can't just ignore that word sine and call it x over x. Like that doesn't work. So then instead, I've got to know, like, okay, is there a positive or negative, direction that it's pointing? And I've got oscillation on top and infinity on bottom. So if I'm plugging in infinity, it just all of it, like nothing seems to work for solving. So in that case, when you're absolutely stuck, I want you to apply the squeeze theorem. And since we had ice cream on that day, we have to remember it. So squeeze theorem, when you have a tough expression, you can make up an expression that's below and above. And if the below and above have the same limit, then yours has the same limit. So we focus first on the numerator. And we think about the graph of sine x. Sine x is bound on the bottom by -1 and on the top by 1. The question we did on this on our classwork page, 2 minus cosine x. Remember, we had cosine, flip it over, and up 2. You had to think about that. This is just sine x, just -1 to 1. So if I set up this inequality, -1 less than or equal to sine, less than or equal to 1, that is a true statement. So I'll look at the numerator first. Then I'll look at the denominator, which is divided by x, and I give all 3 of these the same denominator, so I'm not changing the value of the inequality. And I've now sandwiched my equation in between 2 other equations. So I'm going to try to take the limit of those other 2 and see if I get the same thing. And hopefully it will work. So limit as x goes to infinity of -1 over x, and also limit as x goes to infinity of 1/x. Now I get to use my horizontal asymptote rules. Those are both bottom heavy. They both go to 0. And if the smaller and the larger function both have a limit of 0, that means your function in the middle also 0. So those are like the level 10 squeeze problems. Oh, y'all are exhausted. You're like, throw my pencil down. Question.
My scheme down, and also about like. Basically.
You have to check. Is it always going to be 0? I mean, it probably is a lot, but you have to check it. Oscillation over infinity is not a fixed.
Oh.
Right. You'll do that. You'll apply this principle of BC calculus a fair amount, where sometimes you just have something you can't tell like what the asymptote is, so then you got to squeeze it between two others. Oh, okay. So there was a coefficient attached to the sum that says 3. That makes your graph 3 times taller. And so that impacts your lowest and highest numbers. So then this would have been -3 and +3. Now, I still end up with the bottom heavy there. So it still would be 0. All right. What are we doing next? Okay, we have classwork on Canvas next. So you need a piece of paper. I think I ran out of paper. Maybe there's some paper there at the center table. I believe it's 5 questions. I'm gonna get that turned in first. It is, yes. You shouldn't have it. What time is it? You still have like almost 30 minutes and it's 5 short. Yes.
How you just all.